Hello, everyone. This is Team 3's drinking water project. My name is Celeste.
My name is Jamie.
My name is Elizabeth.
My name is Daniel.
My name is Tiffany.
Here is the agenda of our project. So the City of Plymouth, England has tasked Team 3 to design a water treatment plant to meet the increased potable water demand of the population in 20 years. Plymouth currently has a population of 262,100 people, and it is estimated that the city will grow by 6% in the next 20 years to a population of 277,826 people. The projected 20-year drinking water demand is approximately 11 megagallons per day, and the project location is at the River Plym in the United Kingdoms, which is a freshwater river with multiple tributaries. Next, Jamie will be talking about the first step in our water treatment plant design.
Thank you, Celeste. The first part of our design is coagulation, which is often the first step in the water treatment process. In the process of coagulation, a chemical coagulant is added to the water and it is flash mixed for thorough distribution. The chemical coagulant precipitates solids in the water and prepares the water for the next stage of flocculation. And together, these two processes aid in the removal of contaminants. Next slide, please. So for our design, we have 4 circular tanks positioned in parallel, with the dimensions of each tank being 10 feet high with a 10-foot diameter. The capacity of each tank is 345.4 cubic feet. And we use the equation 2.6.1 to find the water power and help us select a motor of 2.2 kilowatts at 80% efficiency. And then on the right is a side view of one of the tanks, and it's showing the inflow at the bottom and the outflow coming out of the top. And next, I'll hand it over to Tiffany to talk about flocculation.
Okay, thank you, Jamie. So flocculation is a process by which a chemical coagulant will be added to the water and acts as a bonding between particles, which helps create larger aggregates, which will make it easier to separate in the later treatment process. So for our flocculation system design, we had to design for 11 MGD flow, which will consist of 4 tanks, with each consisting of 3 stages. And then, so our detention time of the vertical shafts will have a design criteria of 30 minutes. And then, so based on that, our tank volume was 7,654 cubic feet, and then the dimensions being 2,551 cubic feet of for each volume per stage, and then a width and a length of 12 feet, a height of 20 feet, and then for our flocculator blade, we decided on a diameter of 5 feet, which was picked due to it meeting the geometric ratio standards. And then based on that, for our flocculator motors, for stage 1, we got 1.01 horsepower. Stage 2, we got 0.25 horsepower. And then for stage 3, we got 0.06 horsepower. And then handing it off to Elizabeth, who will talk about sedimentation.
Sedimentation is the third step in our water treatment process. It's the process of removing solids from suspensions by gravity, and the particles that begin to settle will be known as our sludge. Next slide, please. Our sedimentation will consist of 2 rectangular tanks, each with a tank volume of 64,350 cubic feet. It will also have a weir of 99 feet and a weir loading rate of 3,946 gallons per minute per feet, meeting the design criteria of 10,000 and between 10,000 and 20,000. The sludge collection will be a chain flight system with a 75% efficient 6 horsepower sludge withdrawal pump based on the pump head of 60 feet and a sludge flow of 305.6 gallons per minute. And next, we'll go into the 4th step of our water treatment process. Go ahead, Daniel.
Thank you, Liz. The next step in our plant's design is filtration. Using physical filters, the remaining floc and other particles can be filtered out. Using a dual media design of sand media and anthracite, the filtering system is able to clean itself through backwashing the media with previously filtered water. Over a 2-day period, only 0.31% of the filtered water is used for backwash, which meets our standard of less than 6%. Using the equation seen below, we can determine the 4 filter cells are needed for the filtering process. For each cell, we determine the length to be 32 feet and the width to be 11 feet, and the surface filter area to be 352 feet per cell. For our backwash rate, we found our backwash rate to be 18 gallons per minute per foot squared. Now on to Jamie for disinfection.
Thanks, Daniel. Disinfection is an important part of the water treatment process because it deactivates disease-causing pathogens in the water and allows the water to be suitable for drinking and other uses. Our design has 9 tanks, and each tank has a 1-ton capacity each. In calculating this, we use the maximum chlorine required value, which is 1,147 pounds per day. And the reason that we use the max chlorine value is for redundancy and to ensure a sufficient treatment, since this is a crucial step in the treatment process. Next slide, please. Our chemical facilities for this project involve the chemicals alum and cationic polymer. Following the design criteria of 2 tanks for each chemical, we calculated an alum required storage volume of 7,135.6 gallons per tank and a cationic polymer required storage volume of 163.2 gallons per tank. And then from this, we were able to do a product selection of 8,000 gallon and 200 gallon tanks from Snyder Industries. Next, Tiffany is going to talk about our clear well design.
Hey, thanks, Jamie. So for the clear well, it's of the proposed water treatment, it's just where the storage tank facility is where the treated water will be placed after the filtration and disinfection process. And then for our design, it will consist of 2 circular steel storage tanks with a detention time of 12 hours. And then so based on that being determined that our tank diameter will be 137 feet, and then our clear well area will be 18,769 square feet, and then the volume of the clear well will be 506,763 cubic feet. And based on that, we're going to have a water height of 27 feet. And then moving on to Elizabeth, who will be talking about the hydrologic profile.
Thank you, Tiffany. Below is the hydraulic profile of our proposed water treatment plant. It begins at our pump at 229.76 feet. It continues to the coagulation process at the elevation of 271.73 feet. It goes on to the flocculation process at the elevation of 269.30 feet, and to the third process of sedimentation at the elevation of 266.55 feet, and to the fourth process of filtration at the elevation of 256.14 feet, and finally our clear well at the elevation of 255 feet. We'll now move on to our sludge drying bed design, covered by Daniel.
Thank you, Liz. Another element of our water treatment plant are the drying beds for sludge. These take the settled flock from the sedimentation tanks and allow them to dry so the solid waste can be removed from the plant. For our design, we have 4 drying beds with an estimated sludge quantity of 100,046 to 234 pounds and an application rate of 8.19 pounds per foot squared. For our dimensions, on the right, we have our technical report, which shows 135 feet as the length and 35 feet as the width. And next, we're handing off to Celeste for the pump station.
Thank you, Daniel. For our pump station, the specifications that we calculated were that the inlet was 26 inch in diameter and had a velocity of 5.54 feet per second. The outlet had a 22-inch diameter and a velocity of 7.75 feet per second. The friction losses of the inlet were 0.613 feet. The total dynamic head was 50.854 feet. And the pump that met our specifications was a mixed volute pump, which had an efficiency of 86% at 885 RPM. Finally, I'll hand it off to Elizabeth, who will be talking about the project cost.
Thank you, Celeste. So our water treatment plant comes to a total cost of approximately $77 million. These expenses include all treatment processes and its components. It also includes the administration, laboratory maintenance, legal, and engineering construction costs. And this will mark the end of our presentation. Thank you.
Yay. Good job, team.